All right, hello, welcome back. So in the previous videos, we looked at the dynamics of rigid bodies in 3D space. And we were working with Newton's equations, F equals ma, and the extension of that in rotational domain with Euler equations. So before, up to here, we were looking at Newton-Euler mechanics of rigid bodies, which, as we had seen before in the case of the particle dynamics, these Newtonian dynamics is essentially we are looking at three-dimensional spaces, vectors in these three-dimensional space representing positions, velocities, accelerations, and the equivalent in rotational domain, and vector of forces and vector of moments create these accelerations, and we could find the derivatives of velocities and angular velocities using Newton and Euler equations. Now we are kind of changing our perspective a little and looking at Lagrangian dynamics. So unlike Newton-Euler, where everything was in three-dimensional space and we had many vectors in 3D, in Lagrangian, we have a single vector in a larger dimension, like an n-dimensional vector in our generalized coordinate space or the configuration space. So we will be looking at Lagrangian dynamics for a rigid body for now. And before getting into the equations, I think it's useful to go back to the basics and refresh our memories what we were doing with Lagrange and generalized coordinates, and we can see how it easily extends to rigid body dynamics. Okay, so as a maybe recall. So we had a system of particles before. So I'm just drawing a bunch of particles, and there were some, I don't know, constraints between them. There were different joints and distances that were fixed. So we had a bunch of particles, a bunch of constraints. So in this situation, if we wanted to write the equations using a Lagrangian perspective, we needed to have generalized coordinates, coordinates Q's, that these Q's had to have this property, or the collection of all these Q's had to have this property that if you tell me the Q's, I should be able to understand where every single particle in the body is. So these Q's fully do it all sorts of emphasis, fully describe where every particle in the system is, every particle in this, the sentence doesn't make a lot of sense, is in 3D space, or in a space, in 3D space. So generalized coordinates, the set of generalized coordinates had to satisfy this property that fully describe the system. And if we had this, and if we could write T and V are kinetic and potential energy as functions of Q and Q dot. If you had these set of generalized coordinates and these, and we could write kinetic and potential energy as a function of those, then our life was so easy. We could use d over dt of partial L partial q dot I minus partial L partial qi equals possibly these q's or q primes. Q prime, let's call it I. And this was how we constructed the equations of motion for this system. So for each generalized coordinates, we had one equation. Okay, that was before. Now we have a rigid body or a system of rigid bodies instead of particles. Bodies that can not only move in 3D space, but also rotate. The good thing about this perspective of system of particles it is extremely generalizable in the sense that any rigid body or a collection of rigid bodies are essentially, at the end of the day, a system of particles. The only difference is that all the particles within a rigid body are constrained to remain in fixed positions relative to each other. So in other words, we don't have to do anything for distinguishing a rigid body and a non-rigid body or a collection of particles. They are identical, they are the same thing. All we need to do is define a number of variables that using those we can fully describe where every single particle in the body is. And then from there we can easily write equations of motion. So let's so for rigid bodies, let's go here. Rigid bodies. So let's look at I don't know, two examples. A single rigid body. This is not good. A single rigid body. So I have this rigid body. It is consists of infinite or infinite-ish particles within it. The only thing I need to do is find a set of variables that if I know those, I can know exactly where each of these little particles within the body is. And for instance, something we can do is take position of one particle in the body and let's do 3D space, position of this particle in 3D space, and the orientate, how the body is oriented in a space at this point. And from these information, I should be able to know, given the geometry of the body, which I assume is known, I should be able to know how exactly in space is any individual particle. So essentially, in this simple example, 3 position variables plus 3 rotational variables should be enough to fully define the configuration of this system of particles. And from there, we should be able to hopefully define the kinetic energy and potential energy, and then use Lagrangian to find the equation of motion. And coincidentally, in a rigid body in 3D space, 6 degrees of freedom, we had discussed it before, more or less 3 rotational degree of freedom and 3 translational degree of freedom. And these numbers directly correspond to those. So in principle, I should be able to write 6 set of Lagrangian equations of motion for a rigid body. Another example that could be even simpler, you can consider a collection of rigid bodies. Oh, this is not great. So this is one body. I have one axis attached to that. One body here, another axis. Oh, this is not great, but I hope it makes sense. So this base can rotate about a vertical axis, and my two links can rotate about their pivots or their revolute joints. And this is a 3 degree of freedom robot that is very common. I have one of those in, I have two of those, two kinds of that robot in my lab. So in this case, I only need to describe 3 rotations, this Q1, Q2, and Q3. And I should, in principle, be able to write the kinetic energy of all these bodies only as a function of these 3 variables and their derivative. And from there, we can define the equations of motion. So do I write anything here? This cannot be, this can be anything besides a robot, like a car suspension system or the human body. I'm just trying to think what I can write. Let's call this system of rigid bodies. Rigid bodies. These, I just need to write my T and V and consider it in Lagrangian in functions of Q and Q dot. If I can do that, I'm set. So the only last thing I want to discuss here is, I have already mentioned it, but maybe more explicitly, to reiterate a couple of notes. So Q's, to be useful in a Lagrangian mechanics sense, Q's must fully describe the configuration of the entire system, the configuration of the entire system. Let me go a little further down so it doesn't mix up with that example. So the first requirement on how we define these Qs is that these should contain enough information for someone to go and be able to calculate every position of every particle. It is possible to have more information than that. So I have more Qs than necessary. And in that case, I would have some constraints between the Qs, and we can use all the constrained Lagrangian equations that we had before. But this is the minimum requirement. The second one is, the second kind of requirement is that T, or the kinetic energy and potential energy, but kinetic energy is trickier, must be written in Q dots. Q dots. So this one may or may not seem obvious, But for instance, let me show you what we have done so far and why it is not super obvious at some point or at times. So to define positions or orientations in a rotational sense, so let me do it like this now. Examples, or I don't know, example dots. So for orientation, I can use Euler angles, for instance. Euler angles psi, theta, and phi, for instance, in that z, y, x example that we had. These could be my Qs, Qi, Q1, Q2, and Q3, because they describe the configuration at the position level. But for kinetic energy, at least the formulation we had used before, is 1/2 omega transpose I omega. And this formulation, I have written T, the kinetic energy, in functions of omega. So 3 omega, omega x, omega y, omega z. But these omegas are not my derivatives of generalized coordinates. So to be able to use these variables, Qs, in a Lagrangian form, I should write my kinetic energy as a function of the derivatives of these generalized coordinates. And we will see that in the next video. It's not too difficult, but we need to remember what we are doing or where we are going with this. So just to recap, we can do everything we have done so far to write equations of motion using Lagrangian mechanics. The only two requirements that we have is find a set of generalized coordinates that fully describe the configuration of the entire system, and then we should be able to write the kinetic energies as the function of those derivatives of generalized coordinate. So in the next video, let's look at the Lagrangian mechanics of just a single rigid body. Now we can take it from there. All right, enjoy.